Hello everyone, and thanks for watching Edupedia World videos. In this video we'll begin our discussion of the nucleus, which is at the center of the atom and contains neutrons and protons, which together are referred to as nucleons. Now there are some masses of these which you may need to remember, but mostly in the examinations they'll be given to you. The mass of these three particles, neutrons, protons and electrons. The mass of a proton is equal to 1.6726 into 10 to the power minus 27 kg. That is also equal to 1.007276 U. U is the universal atomic mass unit. We'll see what that is in a moment. And that is also equal to 938.27 mega electron volt per c squared. I'll tell you what this is in a moment as well. The mass of a neutron is equal to 1.6749 into 10 to the power minus 27 kg. That is equal to 1.008665 U. We see that the mass of a proton is slightly greater than the mass of the neutron. And the mass of an electron is 9.1 into 10 to the power minus 31 kg, much smaller than the mass of either the proton or the neutron, which is also equal to 0.000548 U, and which is also equal to 510.99 keV per c square. Now, first of all, what is this M and K? M stands for mega electron volts and K stands for kilo electron volts. 1 mega electron volt is equal to 10 to the power 6 electron volts, and 1 kilo electron volt is equal to 10 to the power 3 electron volts. Right. Now let's look at what this whole term is, mega electron volt per c square. In nuclear and high energy physics, it is generally customary to represent mass in terms of energy units using Einstein's equation E is equal to mc square. So when we say that the mass of a proton is equal to 938.27 mega electron volt per c squared, that just means the mass of a proton multiplied by c squared, or the energy due to the mass of a proton, this is the rest mass energy, is equal to 938.27 mega electron volts, which means this is 938.27 multiplied by 10 to the power 6 electron volts, or multiplied by 1.6 into 10 to the power minus 19 joules. So by specifying this particular thing, we can just take c squared to the other side and we know the rest mass energy of the proton, or this is just another way of telling the mass of the proton. What is 1U? 1U is the universal, or sometimes called the unified atomic mass unit. And its value is equal to, you've probably seen this before, 1/12 of the mass of neutral C12, that is the standard carbon 12, which has 6 protons, 6 neutrons and 6 electrons. So, for example, if you look at helium, the mass won't exactly be 4U, it will be something near 4U. If you look at boron, the mass will not exactly be an integer times U, it will be approximately an integer times U. But carbon is the only atom for which the mass of neutral C12 is exactly equal to 12U. Because the definition of 1U is 1/12 the mass of neutral carbon atom. Right. And this is the neutral carbon atom in its lowest energy state. We've seen that atoms can go on to higher energy states by absorbing energy. So this is the mass of neutral C12 in ground state. Right. So these specific values up to 4 or 5 decimals are important because any slight change in mass can actually release a lot of energy, because the equation E is equal to mc square has this big factor of c square. So even a very small change in mass in an equation will end up releasing a lot of energy. That's why it's important to know these values to a large number of decimal places. Now let's look at how nuclei are actually represented. The number of protons Just for an example, a nuclei could be represented as 209 Bi83. This is the representation of the nucleus of the bismuth element. So there are some numbers here. This is the atomic symbol for bismuth. So the numbers here represent different things. The number of protons is also called the atomic number, and it is represented by the symbol Z or Z. The number of neutrons is represented by N, and the number of protons plus the number of neutrons, or the total number of nucleons, is also called the mass number and is represented by A. And obviously A, the total mass number or the total number of nucleons, is equal to Z plus N. Now a nucleus is represented as AXZ, where Z is the atomic number and A is the mass number. So when you have 209B83, it means it has 83 protons and 209 total nucleons, which means that the number of neutrons, or N, is 209 minus 83. Right? So generally the number of neutrons is not represented in this because it's not that relevant. The total mass number is relevant when we use delta E is equal to delta M times C square, and the number of protons, or the atomic number, is generally a significant characteristic of the chemical properties of the substance. So that's why this is how a nucleus is represented. X is the symbol of the element, Z is the atomic number, and A is the mass number. Now all the distribution of electrons around the nucleus, and hence the chemical properties of the nucleus, are determined by the atomic number Z. In fact, for a while it was assumed that it depends on the mass number, and then you have some elements, for example nickel and cobalt, where the atomic number is in the inverse order in which the mass number is, and if you arrange them in the periodic table according to their mass number, it did not give correct results. And once you decided that they need to be arranged according to the atomic number, then it actually started making sense. So that's when we realized that the chemical properties are completely determined by the atomic number. The mass number does not determine that at all. Now there are some nuclei with specific same parameters, other parameters different, and we have special names for them. So nuclei with the same number of protons, that means Z is the same, but A will be different because N will be different. They are called isotopes. Then there can be nuclei with the same number of neutrons. That means A minus Z is the same. It means N is the same, but N generally we don't use. A and Z are the important things, and they are called isotones. And then we have nuclei with the same number of nucleons. That means total A is the same, but Z and N could individually be different, and they are called isobars. And all nuclei with a particular value of Z and N are called nucleides. So if you say 239U92 nucleide, it means all the nuclei which have 239A and 92Z. Now the next question when you start studying a nucleus is to understand how the nucleus stays together. Because the nucleus, if it's just a bunch of protons and neutrons together, like this, then the neutrons will not exert any Coulomb force on each other or on the protons because they don't have any charge, but the protons will exert repulsive force on each other. So if only the Coulomb force was acting, then the nucleus could not stay as a stable entity, because due to repulsion between protons it would break apart. So the only conclusion is there must be another force acting within the nucleus which must be stronger than the repulsive force of the protons with other protons. And this nuclear force is called aptly the strong nuclear force. There is a weak nuclear force which we'll see in the next video when we move on to radioactivity, but the nuclear force which keeps the nucleus together is called the strong nuclear force. Now we'll see some properties of the strong nuclear force. The first is that they are very short ranged. That's why you never see evidence of nuclear forces in your daily life. They generally are effective up to a distance of 1 femtometer, which is 10 to the power minus 15 meters. And this is approximately the radius of a nucleus. So if you take in nucleons and separate them by a distance greater than 1 femtometer, then the nuclear force is not very effective and the Coulomb force starts taking over. But for distances smaller than 1 femtometer, the nuclear force is much stronger than the Coulomb force. Second, like I said, it is much stronger, roughly 100 times stronger than the Coulomb force or electromagnetic forces. The range up to which the nuclear force is valid, around 1 femtometer, is called the nuclear range. And if we take nucleons to a distance smaller than the nuclear range, the strong nuclear force dominates, and if we take them further apart than the nuclear range, then the weak nuclear force dominates. The third, it is always attractive. And fourth, the most important property of it, they are independent of charge, which means the force between two protons, nuclear force between two protons, is the same as the nuclear force between a proton and a neutron, or between two neutrons. So if you have, let's say, some protons and some neutrons, then the protons will be repelled from each other due to the Coulomb force. But if the distance between two protons is smaller than the nuclear range, then they will also attract each other due to the strong nuclear force. Right? Don't be confused by two protons attracting two separate forces on each other. They also obviously attract a gravitational force on each other, but that is extremely small. Right? We've seen that gravitational force is pretty much negligible compared to electromagnetic forces. So two protons exert a nuclear force which is attractive and a Coulomb force which is repulsive. If the distance between protons is within the nuclear range, then the attractive nuclear force dominates, and if it is farther than the nuclear range, then the repulsive Coulomb force dominates. Not only that, but neutrons and protons exert an attractive force on each other too, and two neutrons exert an attractive force on each other too. So this strong nuclear force is responsible for the nucleus not breaking apart. Right. Now, when you have light nuclei in which the mass number is small, then the neutrons themselves and the neutrons with the protons and protons with protons have sufficient attractive energy by the strong nuclear force that they can actually keep the nucleus together. But when we start having very big nuclei, I'm just going to draw it like this, with range of hundreds of nucleons. For example, the uranium nucleus has 238 nucleons total. Then the nucleons at the end, whether it's neutrons or protons, the distance between them is more than the nuclear range, and so the Coulomb force becomes more dominant of the protons and protons. It becomes more dominant over the strong nuclear forces. So that means that for small a, or also called for lightweight nuclei or light nuclei, the number of neutrons is approximately equal to the number of protons, because the Coulomb force is pretty much dominated by the strong nuclear force. But when you have large a, or heavy nuclei, then the number of neutrons becomes much greater than the number of protons, because neutrons can exert only an attractive strong nuclear force on each other, though protons can exert attractive and repulsive forces. So as the distance between nucleons, the average distance between nucleons increases, the strong nuclear force becomes less and less dominant, and so to keep the nucleus stable, we need to add more number of neutrons. The more neutrons there are, the more attractive force there is. The more protons there are, we can't say anything because protons attract both attractive and repulsive forces. So for light nuclei, generally n by z is approximately equal to 1, but as you go around heavy nuclei with of the order of 100 nucleons, n by z generally evens out at 1.6. So that's why when you have an atom like 12C6, it has 6 neutrons and 6 protons. But for 238U92, it has 92 protons and 238 total nucleons. So you can see that the number of neutrons is much larger. It's 138 plus 8, 146 neutrons. Right, so 146 neutrons versus 92 protons, because the more neutrons there are, the more the strong nuclear force will be active. The next property of the nucleus we need to understand is the nuclear radius. Now if you remember from one of the previous videos, we already know that the nuclear radius has to be much smaller than the atomic radius, because that was explained by Rutherford's experiment in which he threw alpha particles at a thin gold foil. And the fact that 1 in 8,000 alpha particles was deflected by a large angle showed that the nucleus is positively charged but has a very small volume. The radius of the nucleus generally goes as r is equal to r naught a to the power 1 by 3, where a is the mass number of the nucleus and r naught is a constant whose value is equal to 1.1 into 10 to the power minus 15 meters, or 1.1 femtometers. And we just saw that the nuclear range is approximately 1 femtometers, so that's why for nuclei the nuclear range is stronger than the Coulomb force, but in your daily life you never really see any evidence of nuclear forces. So with this, just by knowing the mass number, you can know the radius of the nuclei. And one interesting thing here is the volume of the nuclei now becomes 4 by 3 pi r cube, or 4 by 3 pi r naught cube times a, and the mass of the nucleus is approximately mass of the proton times a. Now the mass of the proton and the mass of the neutron are slightly different, but that difference is quite small. So we can say that the mass number is proportional to a, which means the mass by volume, or the density of the nucleus, is independent of A. So just by knowing the mass number, you'll be able to calculate the radius of any nucleus. Now, just like we calculated the binding energy of an electron to a nucleus, the nucleus itself has some binding energy. So the binding energy of the nucleus is a very important quantity in nuclear reactions, and it is the amount of energy needed. The definition is similar to the electrons with nucleus. You can guess it yourself. To separate the constituent nucleons, to large distances. Or another way to put it would be, if the nucleons are initially well separated and they are brought together to form the nucleus, then this amount of energy is released. Right. Now generally the rest mass energy of a nucleus is smaller than the rest mass energy of constituent nucleons. And the difference is the binding energy, which I'll refer to as BE from now on. So for example, we know that the mass of 12C6 is exactly 12U, right? Because that is the definition of 1U. However, we know that the mass of a proton and the mass of a neutron both are slightly greater than 1U. The mass of a proton is 1.007276 U and the mass of a neutron is 1.008665 U. Right. So the total rest mass energy of the combined 6 protons plus 6 neutrons, I'm not going to calculate it exactly. Let's say it's 12.1 U. It should be smaller than that, but let's say it's 12.1 U. Right. So if you take 6 protons and 6 neutrons, initially well separated, and add up all their mc squares or all their rest mass energy, mc square is called the rest mass energy, we've seen that before. If you add them all up, you'll get, let's say, 12.1 U. And when you bring them together to form the carbon nucleus, you see that the rest mass of the carbon nucleus is 12U. Then the difference, or 0.1 U multiplied by c square, is the binding energy of the nucleus. If you take mass to be equivalent to energy, then the greater mass means greater energy, smaller mass means smaller energy. We know that every particle wants to get into its lowest energy state. So when you bring 6 protons and 6 neutrons from infinity close together, the total energy of the system decreases. That's because the 6 protons and 6 neutrons together in a carbon nucleus are more stable than 6 individual protons and neutrons, and the energy released when they combine to form the nucleus is equal to 0.1 U times c square. Now again, this actually would be something like 12.003 something. You can calculate the exact value. I showed you the masses earlier. This was just for illustration purposes. So the binding energy is delta m times c square for any nucleus. Or it can be written as Z times the mass of protons. Z is the number of protons multiplied the mass of each proton, plus N times the mass of neutrons, the number of neutrons multiplied by the mass of each neutron, minus M, which is the mass of the nucleus, times c squared. Right. So this is the total mass of the constituent nucleons, and this is the mass of the atom. And we know that if the atom is stable, then the mass of the atom has to be smaller than the combined mass of constituent nucleons, because otherwise the mass would be greater, and that would mean that it's not stable. Now here I'm going to introduce a concept which I would like you to listen closely, because sometimes it causes students a little bit of confusion because it's subtle, and that is, what do you use here? Do you use atomic masses or nuclear masses? For example, when I said the mass of 12C6 is 12U, that is the atomic mass, which means the mass of 6 protons plus 6 neutrons plus also 6 electrons. The actual nuclear mass of carbon 12 would be smaller than this, because the nuclear mass, the atomic mass would be the mass of, atomic mass would be the mass of 6 protons, 6 neutrons and 6 electrons, or simply the mass of the atom. The nuclear mass would be the mass of just 6 protons plus 6 neutrons. Now we know that will be very slightly smaller than the atomic mass, but when you're talking about these small levels, the energy difference can be a lot, so that's why it's important to be very accurate. So sometimes we use atomic masses in which the mass of the electron is also used, sometimes we use nuclear masses in which the mass of the electron is not used, and they have actually different values. Unless otherwise stated, the mass will mean the mass of the atom, that means including the electrons, right? However, except in very special cases, the actual formula will be the same, because the mass of the electrons will cancel on each side. For example, this could also be written as Z times the mass of 1H1 or a hydrogen atom plus N times Mn. I'm just going to rub this now. This is an important concept, so I hope you understand it. Nuclear mass means the mass of protons plus neutrons. Atomic mass means the mass of protons plus neutrons plus electrons, which in general will be slightly higher than the nuclear mass. So what we took above was pretty much the exact thing, the values of the constituent nucleons, but instead we could write this as Zm1H1. Now this is the mass of not one proton, but mass of one proton plus mass of one electron, right? Because a hydrogen atom has a proton and an electron, plus Mn minus, we could also use the atomic mass here, which would be the mass of Z plus N, or A x Z, where x is the symbol of this nucleus, times c squared. Now you see here what this is the total mass of the nucleus, or m, plus Z times the mass of an electron, because there are Z electrons, and here you have the mass of a proton plus mass of an electron, both multiplied by Z. So actually in this case Z electrons have a mass, and subtracted that with the mass of Z electrons, they both cancel out. So in most cases the mass of the electrons will cancel out, so it doesn't matter whether you use the atomic mass or the nuclear mass, ultimately the mass of the electrons will cancel out. There will be one exception to this in the next video, that will be when we talk about beta decays. And this is where it causes confusion to students, because they assume that these are the exactly same concept. No, they are different concepts which end up having the same value, because in most cases the mass of the electrons cancel. There will be one exception to that rule. Right. So whenever the mass is mentioned, you assume it to be the atomic mass. That means the mass of the neutrons plus protons plus electrons, and in a case like this it would balance. See, NMN is the same as NMN. This whole thing basically is ZMP plus ZME, and this whole thing is basically M plus ZME. So ZME cancels from both sides, and this equation is exactly the same as this equation. Right. So this is important. It will come again in the next video when I show you one specific exception in which the using atomic masses will lead to a different formula than using the nuclear masses, because the mass of the electrons will not cancel out, but in most cases they will. Now the most important quantity in discussing the stability of a nucleus is not the binding energy. You would assume it is, because the lower the binding energy, the more stable it is. And that sort of makes sense, but the actual quantity that is important is binding energy per nucleon. Because it is obvious that the more number of nucleons there are in a nucleus, the greater the binding energy would be. And that doesn't necessarily mean they're less stable. In fact, nuclei such as iron are actually more stable than nuclei such as helium. Right. So binding energy per nucleon is the most important thing, and it is equal to binding energy per mass number. For example, if there are two nuclei, let's say one is 15x, let's say 16x8, and the other nuclei is 32x16, then if this has a binding energy of, let's say, 5 units, then this has a binding energy of 10 units, meaning it's the exact, these two are exact same stability. If it ends up that this has a binding energy of 9.9 units, then this is actually more stable than this one, because the binding energy per nucleon is smaller in this case. Yes, you have twice as many nucleons, but the energy is slightly less than twice as many. Right. So binding energy per mass number, or binding energy per nucleon, is what decides the actual stability. And the general curve of binding energy per nucleon is quite interesting. I'll just draw the approximate curve. This is the mass number, and this is the binding energy. It generally goes something like this. This shouldn't rise up at the end, sorry. It goes something like this. So binding energy per nucleon increases initially, and then after a point it starts decreasing. And this point where binding energy per nucleon is maximum is roughly in the range of 50 to 60, and the most stable nuclei is iron. Right. Iron has the least binding energy per nucleon of any elements. That's why the iron nucleus is considered to be the most stable nucleus. That doesn't mean it has a binding energy lower than hydrogen. It has a binding energy way greater than hydrogen, but it has a binding energy less than 56 times that of hydrogen. Right. Now there is a theoretical model to try to explain this curve, and it actually works surprisingly well with respect to data, with respect to experimental arrangements, and now we'll discuss that model, which tries to predict the binding energy per nucleon. So in this we consider three separate factors which contribute to the binding energy. The first is what is called volume energy. That is the energy due to the, assuming that the spheres are tightly packed, Each nucleon has an energy depending on the configuration, and there will be A such nucleons where A is the mass number, and we assume that the energy is proportional to that. So volume energy BV is approximately A1 times A, where A1 is just some proportionality constant. So the energy that each nucleon has a binding energy with respect to all the other nucleons is assumed to be the same for all of them. Now that's not strictly true, because the nucleons at the surface are not completely surrounded by nucleons. So they have lower energy, and we need to subtract a little bit of energy from that. So the next one is surface energy, which takes into account the fact that not all nucleons are completely surrounded by other nucleons. Some nucleons are on the surface and they're only surrounded by nucleons on one side. So there will be a decrease in energy, and the decrease in energy will be proportional to the surface area. The surface area will be proportional to r square, or proportional to a to the power 2 by 3, because the radius is proportional to a to the power 1 by 3. So this is Bs, and it is approximately minus a2 a to the power 2 by 3. A1, A2 and the next A3, they are just constants which will be chosen according to our convenience. Now the third is the Coulomb repulsion, which will again reduce the energy because the protons will try to repel each other and try to break the nucleus apart. And this will be inversely proportional to R, because the Coulomb potential is inversely proportional to R, and it will also be proportional to Z into Z minus 1 by 2, because there are Z into Z minus 1 by 2 pairs of protons. You've probably seen this thing before in your permutation and combinations class in mathematics. This is basically ZC2, the number of ways there are of choosing a pair out of Z protons. That's Z proton. You choose the first proton out of Z, you choose the second out of Z minus 1, and you divide it by 2 because you've actually counted pairs twice, in case you choose, let's say, the first proton and the third proton, and you choose the third proton and the first proton. You've counted them as 2, but they're only one pair, so you divide by 2. So this is called the Coulomb repulsion, and it is approximately minus a3 Z into Z minus 1 by a to the power 1 by 3. We've assumed this constant 2 into a3. So what that tells us is the binding energy should be something like a1 a minus a2 a to the power 2 by 3 minus a3 Z into Z minus 1 by a to the power 1 by 3, which means the binding energy per nucleon will be B by A. That will be equal to A by 1 plus A2 by a to the power 1 by 3 plus this will be 4 by 3. And this, after choosing appropriate values of A1, A2 and A3, gives a very good agreement with the curve we just saw, which tells us that the binding energy per nucleon initially increases, it reaches a maximum stability at iron, and then it starts decreasing, which means both higher and lower mass nuclei than iron are relatively less stable. This is one of the reasons we have both nuclear fusion and nuclear fission. Nuclear fission means one heavy nucleus separating into two middleweight nuclei because they are more stable. Nuclear fusion means two light nucleus combining to form a middleweight nuclei, again because they are more stable. The most stable are the middleweight nuclei because they have a binding energy per nucleon that is the lowest. In the next video, we'll start studying about radioactive decay and the three main processes by which unstable nuclei decay: alpha particles, beta particles and gamma rays. Thank you.